Hello and welcome back. Today we're going to talk about a reaction called the dehydration of alcohols, also called the acid catalyzed dehydration reaction. And here we have an alcohol substrate, so that just means something with an OH group on it. And our reaction conditions typically involve something like H2SO4 and heat, concentrated H2SO4. So sometimes we actually put the abbreviation here for concentrated H2SO4 and heat. So what we have is a very strong concentrated acid. And what happens is the alcohol gets converted to an alkene. So I'm going to have a double bond here, and I'm going to get an alkene product. So we've lost the OH group, but remember, to make a double bond, you actually have to take something off from each carbon. So what did we lose besides the OH? We actually lost an H and an OH. It's that beta hydrogen is also missing from this position. And so, so what is the byproduct here is H2O. So because it's loss of water in this reaction, that's why it's described as a dehydration, right? If you're out in the desert for a long time, you're losing water, you're dehydrated. And so the same thing is happening here with an alcohol. Okay, so let's think about the mechanism. We've learned 4 mechanisms up to this point in chapter 7, SN1, SN2, E1, and E2. Well, first of all, notice we're forming an alkene. So that means an elimination has taken place rather than a substitution. We didn't just replace the OH with something else. We lost the OH and an adjacent proton. So this is not a substitution reaction. It's going to be either E1 or E2. So for an E2 elimination, the bimolecular version, we have to have a strong base come in and attack that beta proton. Do these look like strongly basic conditions? Absolutely not. These just the opposite, right? So we can't have an E2 as well because there's no strong base. Okay, so what is the mechanism? This is going to be an E1. In fact, this is the typically the only example where we'll see E1 is the major product, the exclusive product. Remember, usually we get a mixture of SN1 and E1 products when we have those sorts of conditions. Okay, so let's see if we can come up with a mechanism for this. We have strongly acidic conditions, right? H2SO4. What do acids do? What do acids do? They protonate things. So that is absolutely going to be our first step, is to protonate. Where can we protonate? We can protonate on the oxygen. And I'm just going to write HA to represent a strong acid. That can save me some time in our mechanisms. I'll just write HA, but remember, it's always 2 curved arrows to show a proton transfer. 2 curved arrows to show proton transfer. So I'm going to protonate my oxygen, which gives me 2 protons on that oxygen now and a positive charge. Okay, and what does that do for us? Well, it just turns this into a good leaving group. This is now a good leaving group, because if it left, it would be leaving as water. So that is our next step, is loss of a leaving group. Loss of a leaving group. And how do we show that? That's just a single curved arrow where the leaving group just leaves. Okay, and so not only does that produce that water molecule that we were expecting to form, but what does it give in the position where the leaving group used to be? It gives a carbocation, which is exactly what we expect for an E1 mechanism. Unimolecular mechanisms mean that I'm going through a carbocation intermediate. Okay, and so how do we go from here to the alkene final product? Sometimes it helps to draw the alkene to kind of think of what's the difference here. Well, we have remember, to form the double bond, you have to remove something from each carbon. So we already lost the leaving group. So what's the next thing we have to lose? We have to lose a beta hydrogen. Now this is where a lot of students make a mistake, is to make sure you go to the beta position adjacent to the carbocation. That is the proton that we're removing. I'm going to go to the most substituted beta proton because that is going to lead to the most substituted, most stable alkene. It's always going to be the product formed here. And so that what's our last step? Our last step is to lose the beta hydrogen, which we could also just describe as deprotonate. Deprotonate. So 2 curved arrows for every proton transfer. Whatever my conjugate base, if I use HA in this first step, I used HA over here as my acid, right? And so that means I now can use A- as my conjugate base, just some weak base that's around to do this deprotonation. So I grab that proton and I use these 2 electrons to form the double bond, to form the pi bond. So that is my mechanism for the dehydration reaction. It's a 3-step mechanism to make the alkene, protonate to make a good leaving group, and then I follow my E1 mechanism, loss of leaving group, and deprotonate, meaning loss of my beta hydrogen. So this is always going to form the most stable alkene. Do we describe that as Zaitsev elimination or Hofmann elimination? That is called Zaitsev elimination. Zaitsev's rule is when we form the most stable, most substituted alkene. The way we know it's the most stable is because it's the most substituted. Okay, like any carbocation involved in a reaction, when we have a carbocation intermediate, remember carbocations are capable of rearranging, so that might happen. It wouldn't happen in this case because we had actually we could rearrange first and then eliminate, but it would give the same product. So we don't have to show that rearrangement step. We could just eliminate right away and make it a more direct mechanism. Okay, and so how is it that we made OH a good leaving group? Hydroxide is not a good leaving group. That would never leave in the mechanism like this. But the way we made a good leaving group is by reacting with a strong acid. So using a strong acid like H2SO4, these are always acidic conditions. And that's how we made it a good leaving group, turn it into water. Okay, notice that we had a deprotonation step, a protonation step, and then a deprotonation step. So we used HA here, and we reformed HA as well. Okay, so it is it's catalytic in acid. So that's a lot of times why it's called acid catalyzed dehydration. Sorry, my pencil is losing it again. Acid catalyzed. It will always be acidic conditions. Sometimes we might use phosphoric acid instead of concentrated sulfuric acid, but we use one or the other. Okay, now let me just talk a little bit about this HA abbreviation that I let my students use. HA in this case represents something like sulfuric acid, very, very strong acid. So what would A- be? A- would be the conjugate base of sulfuric acid. And this is would you say that this conjugate base here is a strong base or a weak base? Remember, sulfuric acid is one of our strong acids. It is so strong that it fully dissociates in water, fully protonates water. Well, if you have a strong acid, then its conjugate base must be a weak base, a very, very weak base. So what makes this so super stable? Why is this because it's an O-, but why is it so stable? Because that lone pair is allylic to a pi bond, adjacent to a pi bond, which means it is resonance stabilized. Absolutely. So I can move this this lone pair over. Remember, allylic lone pair resonance is always 2 curved arrows. Lone pair becomes a pi bond becomes a lone pair. And so I could delocalize that charge. That's always a great thing. In fact, is there more resonance? Sure, there sure is. I can bring it down to this bottom oxygen as well. So it's fully delocalized over 3 oxygen atoms. It's hard to get more stable than that. So it's resonance stabilized. Resonance stabilized. That is fantastic to delocalize the charge. So that makes it very, very unreactive. It's almost like a spectator ion. And so that makes it non-nucleophilic. This is not a nucleophile. This is not a nucleophile. And that's why we don't get competition with SN1 in this case. We get exclusively, we get E1 only. I'll write that later. We don't have to write that right now. There's no SN1 competition because we have no nucleophile. We have no nucleophile. Okay, so so that's why we get this outcome when we use H2SO4. So let's compare that to some other strongly acidic conditions like HBr. When we react an alcohol with HBr, remember HBr is a strong acid, so that makes the OH a good leaving group. But it also has bromide, a source of bromide, so it's also a nucleophile. So HBr or HCl is both an acid and a nucleophile. So when we do this reaction, what did we observe? We got a substitution reaction. We got a substitution reaction. We made a leaving group, and then we had a nucleophile to replace it. And so we got a mixture, and the mechanism might be SN1, might be SN2, depends on the type of carbon it's on. And so we get, oh, sorry, I redrew my alcohol a little bit here. So we get a substitution product. Okay, what's different in this new reaction when we just have concentrated H2SO4? We have an acid only. The only role that H2SO4 is ever going to play is protonation. Bam, you're done. That's all it wants to do. So in that case, when you make a carbocation, it has no nucleophile. So the only thing the carbocation can do is deprotonate. So here we get E1 only. There's no nucleophile, so there's no SN1. So just want to compare the difference. I want you to see what the difference is between these two reaction conditions and see why one leads to substitution, the other leads to elimination. So dehydration of alcohols is pretty much the only time we're going to see E1 as the major product. Every other time we have a carbocation, we typically expect to have SN1 either as the major product or certainly as a byproduct. Okay, and this is a perfect opportunity. Looking at these two reactions of an alcohol, we can take an alcohol and do a substitution with HX, or we could take an alcohol and dehydrate it with H2SO4 and heat. This is really a perfect opportunity to talk about making flashcards as a great way to stay on top of organic chemistry reactions. We saw a handful of them in chapter 7. In chapter 8, when we get into alkene reactions, we're going to see just dozens. And so it's really important to have an effective way to study them and review them, other than kind of flipping through your notes very passively or working on specific textbook problems. And so anytime you learn a new reaction in organic chemistry, there's actually 3 flashcards that you could make for that reaction, because they're, you know, a typical reaction has 3 components. You have some kind of starting material, your substrate, you have some kind of reaction conditions, your reagent, your reagents, your solvent, your temperature, whatever, and then there's a product. So one simple flashcard you can make is just kind of the traditional predict the product type flashcard. So actually going out and getting index cards, making this, you could cut them in half if you want, so you have even more to work with. Is you just say, okay, with this starting material and this reagent, what would the product be? And then on the back, you have the product. So this is a really quick and easy way to test yourself on this reaction. But there's 2 other ways that you can test yourself on that same reaction. You can have a starting material and the product and ask yourself, well, what would the reagents be to do this transformation? Or you could even have the reagent and the product and say, well, wait a minute, what did I have at the beginning that would have undergone this reaction? This is really important as we continue to build the number of functional groups that we're learning reactions of. It'll help you remember, oh, concentrated H2SO4, that was a reaction for alcohol substrates. Okay, and these are especially important when we're trying to plan synthesis, plan the synthesis of a target molecule. Practicing with these types of reactions, this is called a transform problem when you're providing the reagents. This is described as a retrosynthesis problem when you're trying to imagine the starting materials for a given synthesis. Those skills are very important to practice, along with just the traditional predict the product. So this is great not only to, study chapter 7, but when it comes time for the, the midterm, when it comes time for the final for first semester, you're looking at all your reactions. You have this nice big stack of flashcards. And then when you move on to second semester, organic chemistry, how do you go and back and quickly and easily refresh your memory and review those first semester topics? You have that stack of flashcards. Okay, so for example, for these two reactions, so this is what we can make 6 flashcards for these two reactions, for reactions with conc H2SO4 or HBr. And so here's our predict the product type reactions. Here's our provide the reagents type flashcards. And this is what was the starting material type flashcards. So what's really cool about flashcards, as opposed to doing something digitally, making your own flashcards means you can literally shuffle them up so that as you now move on to chapter 8 and chapter 9, you can shuffle those all in together. And when you get really good at one that you know very well, you could actually take it out of your stack and focus on the ones just that you really need extra work with. Okay, so so like I said, you can kind of manipulate them and work with them better when they're physical flashcards, and you could bring that stack with you to second semester and continue on with them as well. And you don't need a computer in order to do that. You could just have that little rubber band around your flashcards and bring it with you anytime you have spare minutes between classes, or waiting for the bus. You could use this on the bus stop when you're hanging out and you have a commercial on TV. You could use these flashcards. If you just have a 10-minute time for organic chemistry, this is a great way to use that. So I hope you can start making some flashcards in chapter 7 and keep up that good habit moving forward. All right, thanks so much for joining me.